What you see is an example of an actual reservoir using methods developed by the oil and gas industry. While it is hard to gain a sense of scale, these typical reservoirs are immense, occupying cubic miles of rocks in their largest forms. These reservoirs are therefore capable of storing immense quantities of heat, as well for the purposes of producing power for long periods of time when that power is needed. Naturally, managing large areas is best accomplished by their partition and through the application of geometric principles to achieve the process management. We call these partitions patterns. These hexagonal patterns are shown as they would be applied to the reservoir structure to achieve an effective heat, storage, or retrieval power plant. Now let's take a look at a single pattern which will be used to demonstrate this technology. To access the geologic formation to be used in the demonstration of this technology, we will require the installation of wells, those used to inject water and those used to recover the injected water. The wells will be drilled from a centralized drilling location to minimize surface disturbances. You can see that for our demonstration project, we plan on drilling 6 injection wells surrounding 2 producing wells, there being a redundant producing well installed in the name of reliability. Once these wells are drilled, we plan on beginning the water circulation process. Naturally, the fluids that will be produced from the reservoir will contain contaminants like fine sand grains, scales, and even some oil. These contaminants must be removed from the reservoir circulation loop, otherwise the heating and boiling system, which we will discuss in a moment, will become damaged. Therefore, a contamination removal system will be installed. As can be seen, since eventually the contaminants removal system will be operated at elevated temperatures, we will install heat recovery heat exchangers to greatly increase the GeoTES system efficiency. Once we have begun the circulation of fluids through the reservoir pattern, we can begin to heat the reservoir using solar collectors as shown. These trough-style collectors are extremely effective in their use of surface area and are robust in their structural competence to resist the effects of weather or even earthquakes, and with their ground-level locations are easily maintained. Because these solar heat collectors are the life's blood of the heating process, we must ensure that the collection element is protected from the contaminants previously described as coming out of the reservoir. Therefore, the fluids used to absorb the sunlight's heat are kept separate from the produced fluids, and the heat contained in them is transferred to the produced fluid circulation system by means of a robust, easily maintained heat exchanger. As you can see, as the produced fluids are heated by the solar heating fluids, they heat the formation, making it a huge energy repository. Over time, we anticipate for the demonstration plant this being about 6 to 9 months. The reservoir will become thermally charged and ready for the next stage of the process. As described with the solar heating plant, contamination of process fluids is a reliability concern. So as with the solar plant, the heat in the produced fluids loop is now available for boiling water to make steam for use by a steam turbine. By adjusting the produced fluids loop circulation rate, we can increase or decrease our ability to produce power to meet power grid demands. When the weather conditions interfere with solar heating, as when there's protracted cloud cover, the heat stored in the reservoir remains available for power production. We have determined our power plant can be operated continuously without any sunlight for up to 41 days before the stored heat as shown.